Well, howdy, this is Tom Eckert, CST, coming at you live from ATG USA, North Little Rock, Arkansas. And I wanted to share with you the second flight that we did. Just as a reminder, yesterday we flew a panorama flight of the building. The intention was a 3D modeling so that we could achieve the facades and the scale for building information of the objects and the features of the terrain. And so what we did is we followed up from the panorama with a particular grid mission flight. So just a couple of the components. If you notice, we have the iPad hooked up to the 3DR. Real simple look at the flight plan. All the pictures actually come in. We've got 108 images. Whole flight took, I think it was 7 minutes, 3 acres. And got some really good resolutions. We decided to fly a double grid mission so that it would actually go north-south and then spin and shoot it east-west as well. So the idea to get the surface for the site as well as the improvements that would be the impervious surface, the curb, the grass, what in InfraWorks is going to be called coverages. And so with those coverages, you've got the ability to do your square footage, as well as volume calculations. But remember, everything's in 3D. And so just a little bit of a reminder of what happened with the sensor. This is the solo that was up on both flights. The first one, we actually had the gimbal that was actually at a 45 and 60 degree angle. Remember, 2 loops around on the panorama. This one we set down, and so that the 3-axis gimbal held it at an 8 degree angle of incidence as we're flying panometric. And so we'll show some of the aspects of what that looks like when it's making a turn, why we chose that particular flight pattern, the wind conditions, and go over some of the situational awareness that was used to make the decisions in what the resulting outcomes were. And remember, when you're making these decisions, you're looking to come up with the ground sampling distance, the precisions and accuracies, and the quality prior to putting the bird up in the air. So you've got the ability to choose the method at which you actually fly it. So real simple. Here's all the images. It's just connect to the internet to upload the data on the iPad here. We're going to jump into the individual Wi-Fi connection that we've got. Once that's selected, then we're going to come in here. We're going to just get to the settings real quick. Wi-Fi is going to take the images off of the iPad and upload them to the cloud. And so here it is, Wi-Fi. Confirms that we're on the internet at that point. Then we come in here, go back to site scan. It remembers where we were at. And this now says upload to the 3DR cloud. It says it's uploading the images. And so whole process to move the images from the UAV to the iPad, approximately 2.5 minutes. And we've already got 6 of the images, 7, 8, 9, 10. So probably another 4 minutes to upload it to the cloud. When we do that, we're going to hit pause on the recording, and when we do that, we're going to jump right in and find out how long does it take to process 108 images. Appreciate you watching. This is Tom Eckert, and stay tuned. All right, we're back, and we had a real successful flight. Actually took a couple of them. We are excited about the combination of the 3DR side scan controller with the DJI applications in the airframe. And so we did a little bit of a testing on flying the same mission with 2 different data sets and did some comparisons, but wanted to dial into the site that we actually flew. We're off the Jacksonville Highway here, North Little Rock, Arkansas, and some aspects of the sites, you know, it has got just a little bit of infrastructure. You're dealing with your right-of-way and your power lines, few trees on the buildings, but what we wanted to pick out on this smaller site was the aspect of the improvements and the site for a topographic survey. And so we want to get enough overlap so that it makes sense that the pictures and the images themselves get the quality of data. And so the measure of success on a topographic survey is not the images in the right brain on what you end up receiving as far as coverage. It's a matter of overlap. And so with the overlap, our parcel was basically, to give you an idea, right here to right here. And that was the coverage of the parcel. And I'm going to just change the style here so you can get an idea. Just want it to be outlined. We're in Google Earth right now, just sort of messing around. And in order to get that particular area, you'll need to fly about 60 feet over so that there is an additional image or two that can be stitched together for the surface model. If there is not enough overlap, if there's only one image, then the accuracies and precisions around the perimeter, they dissipate as you move further and further away from the stitching together the orthomosaic. And so the fact is, that's why when you get the orthomosaic is that it's not a good polygon, but it's got some blur in there, especially in areas you notice here in Google Earth that with their image, you can't even see that there's a sidewalk out front here because the image is not planimetric. Plus you have shadow. So this wouldn't be able to be designed. But let's look at exactly what you can get as a design. And let's watch the bird land real quick, and then we will go from there. All right, so that's what it looks like when the UAV actually lands. I got a 4-point landing. One aspect we always get feedback on, boy, that sure was a little rough. You saw some pitch and roll and yaw as it's coming down. And want to explain sort of what's happening is that at 10 meters, about 32 feet, the GPS changes to the analog sensor. So your IMU, your gyro, all of the aspects of the altimeter on how high it is change from a digital signal at 10 meters to an analog signal. And so as it's coming down, also we were right on the face of the east face of the building, and so you've got a little bit of a wind vortex. So as it's compensating, it saves enough battery to be able to have a very methodical landing. It fixes its descent speed so that it's a safe landing. And so what you're looking at is pretty much the operation of fail-safes as it's coming down. And so that's what it looks like. But let's jump into the software now and see what we actually get. The background map is, again, a Bing map that's streamed in. With the images themselves, each one of them come in as a small little indication, a little circle here, of each one of the individual photos. When you click on it, there's the high-resolution photo itself. You can download it by clicking this button here. This is a 3.6 megabyte file. What I'd like to do is also show you some of the aspects of zooming in. You've got an 8-degree angle on your angle of incidence, so that's what the vertical features look like. But the power lines themselves have a little bit of noise. You can see right here that this is a ghosting in of an image. This is some of the aspects of the photogrammetry that when you look at it, you might get a double image. It's a little bit like an echo that comes from the ground as the sensor is trying to rectify. That's why an individual photo in itself, if it's got no overlap, will look just a little bit different. But I want to look at one aspect of the photogrammetry is the moving from an RGB image on the sensor to it's a CYCB, and so with this YCRCB, it changes the red, green, blue pattern. And this is a good example. This is the same curb return, but where there's a shadow, notice a little bit of grainy blurriness when you're on a sort of cloud-covered day. You've got a muted color. The green, the asphalt, and the concrete are a little bit muted. Same curb return now we look and we say, okay, now we can pick out the green color. There's an albedo effect that comes back. It's a brightness. It's a little bit of a glare on the concrete. And then the asphalt is actually a different color. So when you pick out an image, This portion right here on the right-hand side is actually going to look better in the photograph. The cracks, and people call that quality of image, but it's a right brain quality. It's fairly much the aesthetics. It matches what our eyes want to see. We want to see that luminosity, but the information on the right with the cloud, or the information right here on the cloud cover, is going to be a little more muted, but the quality of the data is going to be better, because it doesn't have to try to balance out the white brightness. It can actually pull out the radiometric components of the edge of the grass, the curb returns, and the concrete. So I like to pick out every now and then individual aspects of the pictures, all of them getting stitched together. What you end up with is the orthomosaic. When you click on this radio button here, I'm going to turn the photo off, and this is the orthomosaic that was taken, 108 images. Again, just a quick reminder, the very best way to share this is to click on here, copy this link, and you've put in your shareholders, anybody who would be a stakeholder in the project itself. You can right-click, paste, you can include it in his email link, any way that you want to get this information in their hands, and doesn't matter where they're at, they're looking at the same information online with some simple measurement tools, with your distance calculations, your volume calculations, a real great interface to push that out as far as a proof of concept. This can happen from the field crew, and they're in the field, and they can send it back to the office so that the decision makers, the engineers, the qualified professionals with the licenses can give the thumbs up from their credenza in the office before the field crew leaves the site. Or it can just be for the individual stakeholders that they want to look at the construction progress, or the overlap, or the quality of the data, making sure we got the right zip code. Did we get the right parcel? Enough overlap. And so as we began this, you notice this is our subject parcel. This is the amount of overlap. Even though it was a rectangle, the aspects of, we call this a vignette effect on the orthomosaic, but the information towards the outsides and the edges is not usable, because the camera itself is collecting light through a circular reticle, just like the pupil of your eye. It's creating then rectangular images, and this is what you get. So anyway, the next workflow, as I had mentioned, you can in fact see there's the DJI sitting on the ground right there. And we flew that one up. Want to do a little bit of comparing, contrasting of the data based on the images themselves. We want to be able to look at the metadata. And just a quick commercial for the EXIF file. There's when you right click in any one of the images, when you open up the properties, the details will tell you the sensor. Notice here's our Sony camera. And look at the number of pixels. We're at 350 dpi, where the DJI is going to be pulling in 72 dpi. We've got 5,000 pixels by 3,600 pixels. The quality of the image as an input parameter, every f-stop ISO speed in that, and then of course the latitude and longitude, the assumed altitude, which is really a height above ellipsoid. But that's a whole other screencast to talk about why GPS has a little bit of a challenge with the vertical unless you use ground control points. So anyway, don't forget to look at the properties of the images. Make sure that this is calculated correctly. And when you do, you can expect to open up SiteScan, look at the processing of your data, do some comparing and measuring of jobs if you want, and now the workflow is to export into whatever GIS, Autodesk Civil 3D, maybe a presentation software. You've got a plethora of options for the entire workflow of this particular project. So stay tuned. Next step is to compare the DJI data with the Solo data. And this is Tom Eckert. We are signing off. Hope you have a great day.